Good morning, friends and dear students. I am Dr. Dwivedi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have covered number of topics in engineering thermodynamics. I am in the last phase of this and I am in module 5. Before I start this thing, I will just revisit what we have covered. In module 1, we have covered different properties of the thermodynamic properties like temperature, pressure, volume, entropy, enthalpy. Also the different phase transfer, dryness fraction, critical points, then heat, work. In the module 2, we have seen the second law of thermodynamics. In first law, in the first module, we have also seen the zeroth law of thermodynamics and the first law of thermodynamics, where heat and the work can be converted. The first law of thermodynamics describes about the temperature measurement like thermometers and all. It is a comparison and how to get the temperature. In module 2, we have seen the second law of thermodynamics, which says that full heat cannot be converted to the work and whole work cannot be converted to the heat because there is a entropy, and this entropy has come, and from there we have got the absolute temperature by the second law of thermodynamics, that is called the classical inequality. In that, we have also seen the efficiency, a term, and also we have seen the Carnot cycle. In Carnot cycle, it is the highest efficient cycle on a given high and low temperature range. If you see in module 3, we have seen the psychrometry, dry bulb temperature, wet bulb temperature, air conditioning, humidity, calculation of humidity, and so on. And in the module 4, we have seen different power cycles. In this, we can divide into the two groups. One is the power producing cycles, another is power absorbing cycle. So for the power producing cycle, we can divide it into the two groups. One is the continuous power, another is the intermittent power. So if you see the intermittent, the Otto cycle, diesel cycle, dual cycle, these three are they are not producing the continuous. Out of 4 stroke, they are producing 1 power stroke. But the Brayton cycle, which is a continuous process, every now and then it is continuous power is generated. So it is a rotary type, and another is the reciprocating type. Another is the power absorption or work absorption devices, or the cycle, which is the Bell-Coleman cycle, which is used for the air conditioning and the refrigeration. And this other group, which is called the power producing, they are used for the heat engines like piston engines or the turbo engines. In this module 5th, we are discussing about heat transfer and the gas compression. As of now, I have covered the 2 lectures before in heat transfer, and today in these 2 lectures, the previous I have discussed about the convection and different Fourier equations, Fourier law, then convection, diffusivity, conductivity, and these all things I have discussed in my previous lectures. Today I am going for the second item of this heat transfer. It is called the convection heat transfer, and that I am going to discuss in this class. In today's class, we will be seeing the introduction to convection, types of convection, Newton's law of cooling, convection heat transfer coefficient H, numerical problem 1. Then we will see now what is the convection, and we will go very systematically to define the convection. Convection is the mode of energy transfer between a solid surface and the adjacent liquid or the gas that is in motion, and it involves the combined effects of convection and fluid motion. So convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas. So in this, one solid, one liquid and gas is required, and this liquid and the gas will be in motion and is involved the combined effect of convection and the fluid motion. The faster the fluid motion, the greater the convection heat transfer. So as much fast your fluid is moving, that much convection will be more. In the absence of any bulk fluid motion, heat transfer between a solid surface and the adjacent fluid is by pure conduction. If the very bulk fluid is not there, and if any solid is present with a high temperature, a normal conduction will occur. There will not be any convection. The presence of the bulk motion of the fluid enhances the heat transfer. So if you produce some bulk motion near the surfaces, the transfer will take place between the solid surface and the fluid, but it also complicates the determination of heat transfer rates. So as and when you are putting some bulk motion of some fluid near the solid, then the this complication of the heat transfer will take place. Here this you can see in this diagram that here is a hard block. In this hard block it is a solid, and if you see here airflow, so velocity variation of air. So here at a very low velocity, but here at a high velocity, temperature variation of the air, it will be faster, but here it is less. So as you have the fast velocity near the surface, your temperature variation will be very high, and your heat transfer is also moving in this direction. So this represents the heat transfer from a hard surface to air by the convection method. So the velocity of the air, if you want to cool or hot the surface, is very important for the convection process. Now we will see the types of convection, and we will see that here we have the forced convection and the natural convection. Force means it is you have to create some additional velocity by some fan or some blower or something, then it is called the force. And if it is happening in the natural condition, it is called the natural. So in the forced convection, convection is called the forced convection if the fluid is forced to flow over the surface by external means such as fan, pump or the wind. So convection is called the forced convection if the fluid is forced to flow by some additional means like some fan or pump. You are adding it and you are pressurizing it so that the velocity of the fluid is increased. So it is called the forced convection. Another is called the natural convection. In the convection is called the natural or the free convection if the fluid motion is caused by buoyancy forces that are induced by density difference due to the variation of the temperature in the fluid. So this you can see here. So here it is a forced convection. So here one hot egg is here and you are putting a small fan. This fan is making that it is getting the cool. But if you see here, if you are putting a hot egg and slowly it is cooling down, so it is the natural convection, and here is the forced convection as shown in this diagram. Now I will discuss about Newton's law of cooling, and this relates a specific coefficient that is called the convective coefficient, and here we can see that heat transfer process that involves change of phase of a fluid are also considered to be convection. So here change of phase is also there, then also this thing will be there. Due to the fluid motion induced during the process, such as the rise of the vapor bubbles during the boiling or the falling of the liquid droplets during the condensation, there also these things are applicable. Despite the complexity of the convection, the rate of convection heat transfer is observed to be proportional to the temperature difference and is conveniently expressed by the Newton's law of the cooling. So, this law states that Q dot of convection is equal to HAS Ts minus T infinity. Here H is the heat transfer coefficient. H is the convective heat transfer coefficient. It is a watt per meter square degree centigrade. That is the unit of the H. AS is the area of the surface. Ts is the temperature of the surface, and T infinity is the temperature of the liquid or the fluid which is moving on the surface. AS is the surface area. Ts is the surface temperature. T infinity is the temperature of the fluid sufficiently far from the surface. So that is the Newton's law of cooling. So this is a Q dot convection is equal to HAS Ts minus T infinity. This is the, and it is directly proportional to the area and directly proportional to the temperature difference. That is delta T between the solid and the liquid. Now we will discuss about the convection heat transfer coefficient, that is the H. The convection heat transfer coefficient H is not the property of the fluid. So we have to understand that this H is not the property like enthalpy. It is not that. It is an experimentally determined parameter whose value depend on the variable influencing the convection. So this H is experimentally find out, and which variables, it is dependent upon the variables which influence this parameter, such as the surface geometry, the nature of the fluid motion, the properties of the fluid, and the bulk fluid velocity. So here, geometry of the surface, nature of the fluid motion, it is slow motion or the medium or the high speed, the properties of the fluid, that is the density and other properties of the fluid, and the velocity of the fluid which is there. Typical values of H is given in this table. So this we can see here that the values of this H, that is the convection heat transfer, is given here in this table. Types of the convection: watt per meter square degree centigrade. Free convection of the gases is 2 to 25. Free convection of the liquid is 10 to 1000. Forced convection of the gases 25 to 250. As you can see, it is 200 to 2 to 25, but if you make it force, it is 10 times, it is increased, 25 to 250. Forced convection of the liquid, here is it is the 10, it is 50 to 20,000. Boiling and the condensation, it is 2500 to 100,000 watt per meter square. So boiling and the condensation is very high. Then if you are doing the forced, then it is higher than the free. That also we have to understand. So if it is a free convection, this value of H will be less. If it is a forced convection, value of H will be high. And if it is boiling and the condensation, the value of, when the change of phase, the H will be high. That we have to understand. Now we will see one numerical of how to solve the problem, and we will understand very well about this. So in the question, a 2 meter long 0.3 centimeter diameter electrical wire extend across a room at 1500 degrees centigrade as shown in the figure below. Heat is generated in the wire as a result of the resistance heating. We are using some electrical resistance to heat and the surface temperature of the wire is measured to be 152 degree centigrade. 152 degree centigrade in steady operation. Also, the voltage drop and electric current through the wire are measured to be 60 volt and 1.5 ampere respectively. Disregarding any heat transfer by the radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. So, we have to determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. So, this is the outer surface. Here, what is the H? That we have to find out. All the parameters are given in this diagram. So, let's see. So, we have to see the solution, that the convection heat transfer coefficient, that is called H, for heat transfer from an electrically heated wire to air is to be determined by measuring temperature when steady operating conditions are reached and electric power consumed. When steady operating conditions are reached, the rate of heat loss from the wire equals to the rate of heat generation in the wire as a result of resistance heating. That is, Q dot is equal to E generated, and this E generated is equal to voltage into ampere. It is a electromagnetic EMF, electromotive force, and it is equal to voltage into ampere. So, voltage is given the 60 volt, ampere is 1.5. So, you will get 90 watt energy is used. Now, surface area of the wire AS is equal to pi dl. D is given 0.3. So, it is 0.003 meter and length is 2 meter. So, you will get here 0.01885 meter square. So, this is the area of the wire. So, now using the Newton's law of the cooling for convection heat transfer is expressed as Q convection is equal to HAS Ts minus T infinity. So, from here, Q we have got from here. This is, we got the Q, we will put here, and then we know the AS, and we know, I think, the temperature and all. So, we will get here H is equal to Q dot divided by AS Ts minus T infinity. So, Q dot is equal to 90 watt. Area just now we have find out 0.01885, and it is 152 minus 15 degree centigrade. Ts is given is equal to 152 degree centigrade, and T infinity is given 15 degrees centigrade. If you calculate this thing, you will get the answer that 34.9 watt per meter square degree centigrade. So, this much is the convection heat transfer. We got this much answer. So, we can discuss this issue, that note that the simple setup described above can be used to determine the average heat transfer coefficient from a variety of surfaces in air. Also, heat transferred by radiation can be eliminated by keeping the surrounding surface at the temperature of the system. So, in the next class, we will be discussing about introduction to thermodynamic radiation, Stephen Boltzmann constant, absorptivity, Kirchhoff's law. These are the references which I have taken, that P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition, Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. Any questions you can ask to my email. It is ydivedi@gmail.com. Please do like and subscribe my channel. Also give the comments in the comment box so that I can see the comments and reply you accordingly. Thank you very much. Till then, goodbye. See you for my next lecture, which is going to be on the radiation. Good.
Like, share and subscribe. Hit the bell icon for more updates.